Factor x squared plus 16x plus 64. This is not a difference of squares, clearly. There's no difference here, and there are actually 3 terms. But this is still a special form, and we can still see some perfect squares. X squared is a perfect square, and 64 is a perfect square. This actually fits the form for a perfect trinomial square. Which is as follows. If we have one term, f squared, and then we have another term, I'm going to put this at the end, L squared, and then the term in the middle is twice the product of those two things that get squared, 2FL, then this is a perfect trinomial square because it factors into f plus L times f plus L, or we can also write that f plus L quantity squared. So let's take a look at our trinomial and make sure that this actually fits the form for a perfect trinomial square. If we look at the first term, x squared, that is x squared. If we look at the last term, 64, that is 8 squared. And then if we look in the middle, at the formula, it says the middle has to be 2FL, which means it needs to be twice the product of those two things that get squared. Well, if we look at the product of x and 8, x times 8 is 8x. And if we take twice that much, or if we double it, we end up getting 16x. So that middle term is 2 times 8x, which checks. So we know that this is a perfect trinomial square. And so we can factor that as x plus 8, the first plus the last, times x plus 8. Or equivalently, we could write that as x plus 8 quantity squared. Either one of these is a perfectly acceptable answer. They're both equivalent to each other. Now, the other way you could do this is you could use the unfoiling method. We've got x squared plus 16x plus 64. It's a trinomial with a leading coefficient of 1. So we're looking for two numbers that have a product of 64 and a sum of 16. We recognize that those numbers are 8 and 8. So we can factor this as x plus 8 times x plus 8. And we get the same answer this way as we did than when we recognized it as a perfect trinomial square. So I often get asked by students, why do we need to know this special form if we could have just used the foiling method? Well, there's two reasons for this. One of the reasons is that sometimes we will have very large coefficients that are perfect squares, and it'll be easier for us to identify them as perfect squares than it would be for unfoiling or the AC method when we have really large numbers. But the other reason is that in higher level math classes, in pre-calculus and in calculus, there are several situations where we might need to identify that a polynomial is a perfect square trinomial. These end up being special, and in certain circumstances, we need to be able to recognize those. So by getting a little bit of practice doing that here, we end up preparing ourselves later to deal with those trinomials.